Hi, this is my lab 4 experiment. So this is exercise 1, and this is my circuit. So I have an analog pin going for the end scope and one analog pin for the potentiometer. It's wired up. This is my Arduino code. So I have pin mode input for the end scope pin and the sampling frequency. And I'm reading in the signal for the end scope right there. And I'm reading in the potentiometer value right there, Fs equals analog read. And I'm defining my period dt right there, and my delay is right there. So I'm currently on step H, and you can see that my Arduino code works properly because I have one peak at 0 and then another peak at about 100, and they're clean, and there's a clean sinusoid right there. This is exercise 1. These are the graphs for it. So the first one is 75 hertz signal, 500 sampling frequency, and the second one is 75 hertz and 200 sampling frequency. This is 142 hertz sampling frequency, and it demonstrates aliasing. This is 100 hertz and demonstrates aliasing. These two graphs demonstrate aliasing. The 200 hertz sampling frequency demonstrates aliasing. Both these graphs demonstrate aliasing. Moving on to the 300 hertz signal, all the sampling rates demonstrate aliasing, as seen by here. So that's the 500 hertz one, that's the 200 hertz frequency. This is the 142, and this is the 100 one. This is my work for the summary table for exercise 1. Here we have the signal for 75 hertz. We have 75 hertz on the top, then we have 100 hertz. Moving on to the 215 hertz. Lastly, the 300 hertz signal. This is the summary table of all the calculations. These are our observations for question 1. To summarize the table, you can tell which signal is aliasing or not. So all you have to do is compare the sampling frequency to the Nyquist rate. If the sampling frequency is less than the Nyquist rate, you know the signal is aliasing. You can see down here that 500 and 200 are more than 150, so they're not, but these two are less than 150, so they are. And you can keep going and compare. So in this one, only these two are aliasing, and in this one, the 200, 142, 100 are, and the last one, all of the signals are aliasing. Furthermore, you can see that there's some noise in because of all these different components that it doesn't match up to the theoretical. The experimentals are slightly bit off, like right there, and then right there is slightly bit off. This one matches the power, but this one down here again is slightly bit off because of noise. This is exercise 2, and right now I'm working on the square wave. The only thing different with the circuit in this one is you change it from A1 to P1 to get pulsing one. And then you go to the end scope, and then you turn off A1 and you turn on P1. Then you set the frequency to 10 hertz. And so if you plot it on the VCA, this is where you see the accurate square wave appear range from 0 to 5 volts. And then you see all these different frequencies down here. This is because of the Fourier series. So that 0 term is the A0 in the equation, and all these different frequencies represent the infinite sum of cosines and sines. And depending on if this function's even or odd, it's going to be all cosines or all sines. So that's why you see all these different frequencies and different amplitudes for each of the frequencies. So now doing the triangle wave, you switch it back from P1 back to A1, and then you go in the end scope, and you turn on A1, set that at 10 hertz, and end scope the max of 4.75 instead of 5 volts. You turn that on. You can see the clear triangle wave here. Then we go to the VSA, and then you see the time domain graph. There's a clear triangle wave, and then this is the frequency domain. So in the time domain, you see that it's from 0 to close to 4.75 because that's what the end scope goes through. And then the frequency, you can see that we have a amplitude at 0 because we have a DC offset. And then we have the main frequency peak at 10 because our scope is at 10 hertz for the triangle wave. Then we have these 1, 2, 3, and 4 different frequencies. They're needed to accurately reconstruct the triangle wave signal. Finally, to sum up what I said earlier for the square and triangle wave, here's the paragraph of other observations that I've noticed.